linear
combination and spanning.
Hello, welcome. In this video, I'm going to talk about linear combination, define it, give examples, talk about the relationship with planes, and introduce the notion of spanning. If V is a vector space and V1 up to Vn are the elements of V, we say that the elements of V generate V if given an element V in the vector space V, there exists the numbers x1 to xn such that let E1 to E to the n be the standard unit vectors in R to the n. So E at the I position has component 1 and in the other position it has components as 0. Then E1 to E to the n generate R to the n, given that there exists x which is in R to the n such that x equals to the sum from I equals to 1 to n of xi times ei. That implies x1 times v1 plus x2 times v2 up to xn times vn is a linear combination of v1 up to vn, where v1 up to vn are in the vector space and x1 up to xn are the coefficients. Theorem: the set of all linear combinations of v1 to vn is a subspace of the vector space V. Let W be the set of all such linear combinations and x1 to xn be numbers, similarly as y1 to yn. Then the sum of two elements of W is again an element of W, that is a linear combination of v1 to vn. Also, if C is a number, then the product of C with the linear combination still gives an element of W, that is. And finally, there is a zero vector for which if V1 is a non-zero element of V and also W is an element of V, then the set of elements W plus T V1, where T is a real number, is a line passing through W in the direction of V1. Now, when V has the zero vector and when W equals to 0, the line consisting of all scalar multiples of T times V1, where T is a real number, is a subspace generated by V1, that is, V1 generates V. So, if V1 to Vn are elements of the vector space V and they are non-scalar multiples of each other, the subspace generated by V1 to Vn is called the plane generated by V1 to Vn. It consists of all linear combinations which are if P is in V and S is the arbitrary subset containing all the elements V1 to Vn, then P plus S is the translation of S by P and it forms a plane which is not passing through the origin, hence is not a subspace. The plane is parallel to the elements V1 to Vn. Let S equals to the set V1 to Vn be a set of vectors in the vector space V such that S is a subspace of V. W be the subspace of V consisting of all linear combinations of V in S. Then W is called space span by the vectors V1 to Vn. The vectors V1 to Vn span the space W, or every Vi in W is expressible as a linear combination of Vi. S is a spanning set of W, noted as a vector V is in span S. That implies there exists C in R, for which V is equal to the sum from 1 to n of Ci times Vi. Let S be that and S prime be that be two sets of vectors in a vector space V, then span S equals to span S prime. If and only if each vector in S is a linear combination of those in S prime, and conversely, each vector in S prime is a linear combination of those in S. If each vector in S is a linear combination of those in S prime, then span S is a subset of span S prime. Conversely, if each vector in S prime is a linear combination of those in S, then span S prime is a subset of span S, implying that span S equals to span S prime. This brings us to the end of this video. Thanks for watching. Like and subscribe for more.